The morning session of the conference today. So it's my pleasure to introduce to you Marcelo Avila. Well, he will introduce himself, by the way. And please, Marcelo.
Okay, thank you. First of all, thank you to the organizer for the kind invitation. It's a good opportunity to share my results on one of my favorite topics, that it's Firefly synchronization. So, yeah, about me, I'm Marcelo Ramirez Avila. I'm from La Paz, Bolivia, where I have a position at the Public University of La Paz, whose name is Universidad Mayor de San Andrés. And now I'm working with Teo Carletti in Namur, in the UNAMUR. Okay, so let me introduce the people that are involved in the Firefly collaboration team in chronological order. We can mention to Jean-Louis de Neubourg from the University of Brussels, Gabriela Conde from the University of La Paz, but now at the INPE here in Brazil. The Uruguayan team, Nicolás Rubido, Arturo Martí, and Cecilia Cabeza from UDELAR. And now Nicolás is in the University of Aberdeen. The German people involved, Jürgen Kurz and Nils Bessel from the PIC Potsdam and the Humboldt University, respectively. Stephanie de Piquet from Cienzano in Belgium. And now with Teo Carletti, Elio Tucci from the University of Namur, and the collaboration with Cinzia Tomaselli, Valentina Gambusa, and Mattia Frasca from the University of Catania in Italy. Okay, so this is the content of the talk. Maybe I will, some parts I will pass very quickly, but what I want to transmit is the historical aspect of how we start to study synchronization, and how we derived in some interesting issues that I will refer at the end of the talk, especially related to the response to synchronization. Okay, maybe you see this amazing picture that appeared in Scientific American in 1993 from Strogatz and Stewart, where we can see that we have enormous swarm of fireflies that are synchronized. Okay, so why study synchronization in fireflies? So actually, it's very interesting that the first documented observation of such a synchronization was made by a Dutch physician whose name was Engelbert Kampfer at the end of the 17th century, just some years after the first observation of synchronization, but with a couple pendula by Huygens. So this slide I called evolution of the evolution, because we can consider the evolution of fireflies that in principle the flash of the fireflies constituted just an aposematic signal. It means that it was just to repel the potential predators, to say, don't approach because I'm toxic. And these signals evolved to convert in a sexual signal. In fact, the firefly synchronization evolved as a sexual signal that allowed the fireflies, or that allowed the fireflies to identify the conspecifics. But what about the human thought? So, yeah, after the first observation by Camphor, many people believed that it was just a subjective phenomenon, optical illusion. During several years, some people say that it was an accidental phenomena or that was related to the meteorological conditions. And even in journals as Science, there were many letters indicating that it's Firefly synchronization indeed doesn't exist. But 100 years ago, more or less, the fact that Firefly synchronization exists has been verified, and now it's one of the paradigmatic examples of synchronization. Okay, let's start. I must confess that at the beginning, when I started to study Firefly synchronization, I imagined that just we have some insects that at the beginning they had their own rhythms, and due to their visual interaction, they can synchronize. It's what we understand, and we use this example to refer to synchronization. I remember Professor Ricardo Viana mentioned that. But we will see that it's very interesting to model this behavior. So maybe one of the simplest model has been done by Strogatz, and it's the integrated fire oscillator. That is a very simple dynamical system that each oscillator, each firefly is described by this simple differential equation, and Mirollo and Strogatz introduced a threshold, an upper threshold, and that permit finally the oscillators to synchronize. So here we have an example of two oscillators. The characteristic of the oscillator is that we have a charging stage, and then when the signal achieves the threshold, it discharges instantaneously. Take in mind this word instantaneously, because it will be very important for the understanding of the other models. Okay, so in this simple way, when the oscillator 1 achieves the threshold, it affects the dynamics of the oscillator 2, and the same if the oscillator 2 achieves the threshold, affects the dynamics of the oscillator 1. There is a phase advance, and in this way, the oscillators can become very easily synchronized. So it's why it's called inevitable synchronization. Here, by means of a Raspberry plot, we can represent 500 oscillators, coupled oscillators by using a mean field coupling. At the beginning, each green dot represents the time in which the oscillator achieves the upper threshold. And so at the beginning, all the oscillators are disordered, let's say disordered, and very quickly they synchronize. Okay, so this simple model was a paradigmatic model that has been used to refer to synchronization. It's a very nice model. And the word inevitable synchronization, the phrase inevitable synchronization, has been very important from the historical viewpoint. Okay, so we were interested in reproduce that in terms of some experimental issues. So we construct a very simple electronic device that we called light-controlled oscillators, or simply electronic fireflies. Here's one of the oscillators and a set of oscillators. And it's very simple because this electronic device is composed by two RC circuits, some LEDs, some infrared detectors, and a flip-flop, a very popular flip-flop that is the LM555, working in its stable mode, and with certain characteristic values. For instance, working with the capacitor of 0.47 microfarads, we can carry out experiments that we can measure in the oscilloscope. And if we want to see the firefly effect visually, we must add a capacitor of 10 microfarads. Okay, so what we obtain observing at the oscilloscope is that we have this kind of signals very similar to the integrated fire oscillator. So we have a charging stage, a discharging stage, but this there is a tiny difference comparing with the integrated fire oscillator, because the discharge is not instantaneous. It's very, very short, but not instantaneous. This tiny difference will imply a very distinct dynamics, and we will lose the inevitable synchronization. Okay, so working with the experimental results that we obtained working with the LCOs, the light-controlled oscillators. Here you can find, you can see the situation in which the oscillators are coupled. So we see that they are synchronized. In the uncoupled situation, of course, they will not synchronize. Okay, so based on the experimental results and on the aspects related to the electronics, we construct a model to describe the dynamics of these oscillators. So basically we have two thresholds, an upper threshold and lower threshold. It's not very different from the integrated fire oscillators. And we associated a binary variable epsilon that takes the value 1 when the oscillator is in its charging stage, and 0 when it's in its discharging stage. Remember, the oscillator flash when it's in its discharging stage. Okay, we can solve these equations and find the natural period of oscillation of each oscillator that, of course, are in terms of the electronic components of the two RC circuits. So we can introduce some conditions to explain the flip from the charging to the discharging stage, and vice versa from the discharging to the charging stage. So now if we introduce the interaction among the oscillators, we will introduce this this component beta Ig. That means the action of the LCOJ over the LCOI. So basically, this beta Ig constitutes the elements of the adjacency matrix. So finally, our dynamical system can be described by this set of equations. If we have n oscillators, we have the n equation where we can identify the charging part, the discharging part, and the interaction part. Sorry? Yeah, the interaction occurs just by the pulses of light. When one of the circuits or the fireflies emit a pulse, they act over the other oscillators. It's just by means of light. Yeah, it's very amazing when we presented this circuits for the first time. Yeah, we can achieve synchronization, and people ask it, but they are wired your oscillators. No, it's just they are coupled just by means of the pulse, the light pulses. Okay. Yeah. They actually, yeah, it's each LCO had a sensor in each side. So yeah, of course, we only can make local coupling, but okay. Anyway, we obtained some interesting results. So we validated our model by the experimental results. We carried out several experiments, and yeah, the model worked very well. So at this stage, we started to have fun imagining other situations, like consider an all-to-all coupling under a mean field coupling, or maintaining the distance-dependent coupling. That is what it happens with the LCOs. Okay. Yeah, here we can see, or we can represent the dynamics of the oscillators by a polar plot where the radial part represents the period of the oscillators, and the angular part represents the phase difference with respect to our reference oscillator. In the case of identical oscillators, and in the case of non-identical oscillators, we saw that in the first case, complete synchronization has been achieved. All have the same period, and the phase difference is 0 between them. And on the contrary, for the non-identical case, there are some clusters, and maybe we can wait for a long time to achieve synchronization. But from the realistic viewpoint, whether if we talk about circuits or we talk about fireflies, from the energetic viewpoint, we cannot wait a very big time, because finally the battery of the oscillator, of the LCO, will be discharged, or the combustible of the fireflies will be exhausted as well. Okay, then we worked with some funny situations in which the oscillators can move. So here we have just two situations in which we have random walk. I think it's not working. The other videos are not working. Okay. Yeah. Okay. So what we observe is that the formation of clusters that are not only spatial clusters, but mostly temporal clusters. It's what interests in the case of fireflies. So here we have a static case. There's no motion, and the emergence of clusters we can note by the color code. The same here. In fact, in this situation, the oscillators at the beginning started to move, and then they stopped and stay at rest. And thanks to this, this exploration of initial conditions, finally we attain the complete synchronization, or as in this case with the random walk. Okay, it's very nice to see these small squares to move, but what happens in the reality? The probability of total synchronization is very low, as we will see in the next slide. So working with different arenas, with different size of arenas, and with different number of oscillators, going from 4 to 80, what we have is a distribution of the clusters. We can rank the clusters, and roughly speaking, we have a power-law relation that is similar to the SIP law. Okay, so here we have the value of the power, the value of mu for different size of arena, the different number of oscillators, and we performed, if I remember well, a 100 simulation for each case. Okay, that's what it happens with the LCOs. Let me finish this part with a comparison between the integrated fire oscillators, the Strogatz model, and our LCOs. So in both figures, the upper part represents the dynamics of the LCOs, and the lower part, the second row, represents the dynamics of the integrated fire oscillators. For a mean field coupling in the identical situation, we have that both attain 100% of synchronization, both the integrated fire and the LCOs, with slightly differences, but okay, we can say that in this case, synchronization is inevitable. But when we work with different oscillators, with non-identical oscillators, here's the relative standard deviation with respect to one of the variables that are related to the charging time, to the R lambda, to the resistor R lambda. We see that for the case of integrated fire oscillators, yeah, the synchronization is inevitable, no problem at all. But for the case of light-controlled oscillators, there is a limit in which there is no complete synchronization at all. Well, of course, they can be several clusters, but not a complete synchronization. But what happens if we consider a distance-dependent coupling? So for the case, it's very, very surprising for the case of integrated fire oscillators, considering this type of coupling, even for identical integrated fire oscillators, synchronization, complete synchronization doesn't appear. So, yeah, in this way, of course, if we have non-identical oscillators, the situation is still worse. And then the paradigm that we have inevitable synchronization with the integrated fire oscillator model is not true when we have this kind of coupling. Okay, so now let's start with the the heart of this talk. That it's, okay, as you can see, I talked about synchronization in a generic way, talking about the circuits, the LCOs, considering that Firefly works in a similar way. We believe that they can work in a similar way. But before to read this paper, we didn't think in how to apply it to the real fireflies. So when we read this paper, that is an experiment made by biologists. So the experiment was very simple. They consider a female of a certain species, Photinus carolinus indeed, and they considered some groups of some LEDs that can show a kind of synchronization or quasi-complete synchronization or disordered situations. And what they measured that the female can respond to the males, to the virtual males in this case, in a very nice way when we were in this situation, let's say in a synchronous situation, and as far as the signals became disordered, the response of the female can plummet, and here maybe it's 5% of response. We decided to modify our model considering this male-like flash pattern and test if with our model we can explain this behavior. So we consider the flash pattern of the male, but now we introduce the typical waveforms of the light-controlled oscillators, introducing this quiescent time or this silent time. And of course, for us, the charging stage represent just when the firefly is not flashing. The discharging stage represents the flashing time, that it's represented by these green rectangles. And obviously, the silent time, there is no flashing at all. Okay, we consider all these features, and also we can consider delta phi as a phase delay that plays the role of initial conditions. And okay, it was good for describing the male's behavior, but we have to describe also what happens with the female's behavior. So for the females, we consider that the charging stage was much longer because it's just a flash to respond to the male synchronization. And if we see the waveform are very different between the males and the females, so we can say that the males can be associated to bursting oscillators and the female to a non-bursting oscillator. Here we have the signals, the time in which the flashes are produced for males and for females. Okay, so what we have done is to adapt the model of light-controlled oscillators to these situations. We have to consider the silent time, that it's here. Basically, the dynamics is very similar. And we have to consider as well what it happens when there is the transition from the discharging stage to the silent time, and what it happens in the transition from the silent time to the charging stage. So all these elements have been introduced in the new model, and of course working with real values related to this species of Firefly. Okay, so and one of the most important ingredients is the introduction of this term theta I. That's maybe for those who are the background of physics can be associated with. Can remind you your times of statistical mechanics when distinguishing the partition function between Fermi-Dirac and Bose-Einstein distributions. And this term, theta I, takes the value 1 for the bursting oscillators, or the males. From now, I will use indistinctly bursting oscillators or male, and the same, the non-bursting oscillators or females is characterized by the theta I equal to -1. Okay, so maybe it is good to explain how it affects in terms of the dynamics. So we have here a part of a signal of bursting oscillator, and here a part of a signal of a non-bursting oscillator. So according to this equation, so if the bursting oscillators receives stimuli, it advances its phase, like in the case of light-controlled oscillators. And if it receives a stimuli during its discharging stage, there will be an inhibitory effect, so the discharge will take longer. On the contrary, due to the fact that we have this term theta I equal to -1 for the females, we have that if the non-bursting oscillator receives a stimuli, it will inhibit the charging, and if it receives the stimuli during the discharging, it will accelerate the discharging. So these dynamics lead us to explain, as we will see in the next slides, how it explains the response to synchronization. Just to point out some aspects, we have here two bursting oscillators, two coupled bursting oscillators. We have the signal for the oscillator 2 in cyan, and the pulses represented here, and the same for the oscillator 1 in blue. And we see that very quickly these coupled bursting oscillators can synchronize. And what happened with the non-bursting oscillators? So we have, here we have three different situations. The same, we have the waveform and the pulses. And we can see that after a very long time, we see that in any case, these oscillators can synchronize. So the non-bursting oscillators, they never synchronize when interacting between them. As of course, here we are considering just the interaction of the non-bursting oscillators. Okay, but what happens if the bursting and if a bursting and non-bursting oscillator interact? So we have the bursting oscillator, and it's a signal. It signals, and we have the non-bursting oscillator. So we can see here that the fact that the bursting oscillator is flashing, it inhibits the charging stage of the non-bursting oscillator. But okay, we have some interesting situation. Here, anyway, the non-bursting oscillator can flash, as we can see here. But there are some situations in which the interaction between the bursting oscillator and the non-bursting oscillator finally will inhibit the flashing of the non-bursting oscillator. So there is a kind of oscillation death. There is no response at all. The same in this situation. And it's just due to the dynamics of the system. We are describing the interaction between dissimilar oscillators, and in this case, we see that the bursting oscillators can inhibit the response of the bursting one, the non-bursting one. Okay, here we have other situations. For instance, here we have that the response, maybe it was marked in one of the slides, but this active phase, it means the bursting behavior plus the quiescent time, constitute the phase that the biologists call the phase of the oscillator. So we can see here that there is no, there are some phrases that in which the non-bursting oscillator doesn't flash. The same here. Here we have 2 flashes every 2 phrases. And what happens if we have several non-bursting oscillators? So the action of the bursting oscillator can generate some temporal patterns in the response of the non-bursting oscillators, and even the bursting oscillator can induce the simultaneous response of the non-bursting oscillators. So the previous slides described the dynamics, and what we did afterwards was to try to reproduce the results obtained by Moiseev and Copeland, the paper in Science. And yeah, it's a very simple situation. In the case of Moiseev and Copeland, yeah, we can fix the dynamics of each oscillator, of each male, if you want. And yeah, there's no interaction at all. And what we observe is that in situation in which there is a kind of synchronous signal, the female can respond with a great percentage of responses. And as far as the signals become disordered, the response to plummets, as in the case that has been observed by Moiseev and Copeland. So in this way, we validated our model. And now we can explore many other things, a more realistic situation in which now the males can interact. And so we have at the beginning non-synchronous males, but due to their interaction, they can synchronize, and the synchronization will induce the response of the female. So in other words, we have such a principle in the sense that we have the response to synchronization, that it implies that if we have a population of oscillators that can synchronize and a population of oscillators that cannot synchronize, when we put all together, of course they will interact, this population will still synchronize, but can generate the response in these oscillators, or the oscillators F, that eventually can give rise to some ordered temporal patterns. Okay, here we have some other examples considering 15 males and 5 females. As you can see, particularly in this case, the response of the females are simultaneous. And yeah, let's go beyond the Photinus carolinus, beyond the example that we analyzed. So we consider other Photinus species. For instance, Photinus colustrans, we have this, the features of Photinus colustrans both for the males and both in the females, and Photinus greeni. And considering these values, what we observe for Photinus colustrans, okay, the males synchronize, and when the males synchronize, the female respond. And also for Photinus greeni, with 2 flashes per burst, the males can synchronize easily, and the females will respond. Okay, thank you. So some other examples, considering now oscillators, bursting oscillators with 2 flashes. As you can see, what we generate is different temporal patterns of response. So that was very interesting. We thought a lot about it, and we are still discussing, especially with Jean-Louis Denebourg and now with Theo, about what is the meaning of these terms that we're introducing. Okay, we have the flash rate. We can define the flash rate in terms of this simple relation, but it's more important. Here, it indicates how the females can respond to synchronization, but it doesn't mean nothing about the form of the temporal pattern. On the contrary, this term that we call it for the moment quality of information, they take into account the number of clusters, temporal clusters, and of course, in most of the situation, the flashing rate and the quality of information will be different. As we can see here, if we compute the flashing rate, we have this value. And if we compute the quality of information, we have this value. Of course, if the females respond in every phrase and simultaneously, we will have the quality information equal to 1. So what determines the response to synchronization? Of course, the intrinsic parameters, the time of charge, the time of discharge, and the number of flashes per burst, the coupling strength, the number of oscillators. So we can achieve the response to synchronization with different types of patterns, and eventually this type of patterns can be considered as well as signals to communicate. Okay, we performed several simulations considering for the number of flashes going from 2 to 9, the coupling strength going from 100 to 10 to 100, and the number of the females going from 1 to 9. So we have 288,000 situations. I will refer just, we consider 4 types of interaction that I will mention quickly. For instance, if we consider that just we have a male, we can see as well as this signal could be considered as well as a synchronized male, a set of synchronized males, or just one male. So if we have this kind of interaction, we have the distance-dependent coupling, and we call this situation as synchronizing unsynchronizable oscillators. Here we have a situation in which now the females can interact, and only the males act on the females, and we call this situation enhancing synchronization in unsynchronizable oscillators. We have this other situation in which this oscillator acts on the pink oscillators. We call this the enhancing resonance in unsynchronizable oscillators. And finally, when everybody is interacting, we can say that we call this situation as controlling and synchronizing unsynchronizable oscillators. Just as a glimpse, one of the analysis with the enhancing resonance, we consider here a coupling strength of 10, and then we have the number of females going from 2 to 9, and we compute in terms of the male's number of flashes that goes from 2 to 9. What it happens? What we can observe here is that the flashing rate is, in most of the cases, 100%. But what happens with the quality of information? It's not 100%, except in 2 situations in which the number of flashes per burst is 7 or 9. So it's more or less what it happens with, specifically with Photinus carolinus, the species that we have studied. Okay, just to summarize, maybe you can read that. We unravel the mechanism leading to synchronization and response to synchronization. We extend the concept of response to synchronization. We introduce some other concepts such as the quality of information. We observed multiple interesting phenomena such as oscillation depth, enhancing synchronization and resonance. And of course, the results give us ideas for possible models of opinion formation. Okay, of course, there is dynamical richness that leads to multi-stability. And yeah, there are many ideas about some opinion formation models. And finally, the last challenge that started some weeks ago with the TEOS team is to introduce this response to synchronization to robots. So we are working with some robots that are called EPACs. And yeah, here maybe you can see a film. Of course, for the moment, we are not introduced in the code of the robots the possibility of the interaction leading to response to synchronization in these robots that can move. They are working with the dynamics of a Rosler model, and we introduce a threshold and the robot flashes when it achieves this threshold. So the big challenge is to work with these robots with this response to synchronization. So last but not least, I have to acknowledge the European Union, the European Union's Horizon 2020 for funding my stay in the University of Namibia. So thanks for your attention.
Okay, we have time for questions. Please.
Thank you, Marcelo, for a very nice talk. My question is, I believe 99% of all talks about synchronization starts with a picture of fireflies.
Yeah.
And then in slide number 2, you have the Kuramoto model. So the question is there any way to map this integration and fire models into something simpler, or the Kuramoto model is just not useful at all for fireflies?
Actually, I think that there are several models, not only the Kuramoto models. Ermentrout, Winfrey introduced some phase models. They are useful, but maybe what the take-home message that I would like to give is that the model that we use are validated by experimental issues and consider the fact of the flashes of fireflies, the communication. Yeah, I don't want to say, no, it's not useful to work with Kuramoto model or with other models. But yeah, just say that this model opened our minds to work with different issues. Really, we are working with real fireflies, and now we pretend to extend our model to robot behavior. So, yeah, I don't anything against other models.
Yeah, I have a question.
Yeah.
Thank you. It was very nice. It's a technical question. What if you position one of your circuits too far from the other, like in the limit of the range of work of the sensor?
Yeah, actually, we have a dependence almost as the inverse of the square of the distance. So experimentally, we found 2.11, but yeah, maybe it's due to the fact that the LEDs are not point sources. But anyway, the intensity of the coupling exchange diminished in this relationship. Yeah, so in principle, we can consider that we can go to infinity, but of course it's not doable. Yeah, experimentally, if we want to maintain enough coupling to maintain the synchronization in a set of LCOs, the distance could be around 15 centimeters, or something like that.
Okay, thank you. And what is the effect of the delay? Because there is a delay, right?
There is
a time delay.
The time delay. Yeah, yeah. We didn't consider taking into account that they communicate just by means of their light pulses. So we didn't consider a time delay. Yeah, maybe it's a limitation of the model, but yeah, we.
Okay, any other question? Well, if there is not, let's thank Marcelo again.